Welcome everybody to the second session on program analysis. It's my pleasure to have here Shawn, who will start the session with his collaborators' work on Historia.
So our research is motivated by my antenna pod, or my podcast playing application, Antenna Pod. This is an Android application. And we found a particularly interesting issue in it on their tracker, where a stack trace was reported, just posted online. But very frustratingly for the developers of this application, the stack trace only contains one application method, and all the rest of this is code that actually comes with the phone. It's not code that you have access to when you're writing the application or anything else. And then, even more confusingly, the fix for this is in a completely different callback on destroy. And so the main challenge of our research is how can we help the developer and prove that this fix actually fixes this bug. And as we'll see, this particular issue goes very deep and has some non-trivial properties to it. So let's look into what caused this crash in the first place. An Android application is implemented with a series of callbacks that we'll show in red. The crash happens when this particular callback call is invoked in an unexpected state where the UI is no longer visible, i.e. this act variable is null. And so why this crashes and how it's fixed boils down to why can call be invoked while the UI is not visible. And so we have your phone that has the framework, and it has a whole bunch of stuff going on. But in this case, the call is responding to a background task that loads some media. Typically, this is done off of the UI thread, so you don't make the application unresponsive. And importantly to the rest of this talk, we're going to be talking about the sequence of actions between the Android framework and the application. We call these message histories, and they consist of the name of the callback and arguments such as F. So another event invokes a non-create callback. This event is when you start the view that shows all your podcasts. And in particular, this one calls a method on the framework that, as a dual to callbacks, we call these call-ins. And this goes to the framework with to say start the background loading task. And then we get an unexpected event between these two where the system says, I need memory, clean things up. And this is this callback on destroy sets the activity to null. And this allows garbage collection and prevents your phone from running out of memory. But unfortunately, this means that this particular message history with on destroy and call causes this crash. So how's the application fixed? We have our single line in on destroy that I mentioned at the beginning there. And this blocks this final call. And importantly, this isn't just blocking all background tasks. It identifies the specific background task that causes the crash and stops that. And so the reasoning about this fix not only is about the ordering, but it's about the shared values between each of these messages. And we want to understand this fix, we need to know that this particular sequence of create, subscribe, destroy, unsubscribe, call is not realizable under the real framework. So why is it challenging to prove this in real life? Well, the framework code itself is not something that's available to a developer or to us as people writing program analysis tools. It's full of reflection, dynamic code loading, native code, and also you have to develop this app against a bunch of different versions of the phone. There's probably as many versions of Android as there are people who have an Android phone in this room. So that's what you're developing against. It's not a whole program at this point. So our first overall, or our main overall insight here is that we want to consider what the framework does as non-deterministic and over-approximate as possible. So we initially assumed that callbacks can be invoked in some non-deterministic order with non-deterministic arguments. And then we do the rest of the verification with the goal in mind that we want to prove that this stack trace is no longer possible. And so we look at this assertion and say, can we show that no message history can reach this failure? And so our first contribution is a way of abstracting control flow without the whole program by considering these message histories. And so the next question is, do you need to model the whole framework? And this becomes important with Android because there's tens of thousands of callbacks and hundreds of thousands of methods that could affect the order of these callbacks. And so, like, writing down a model of this whole thing is a Herculean task. Nobody wants to do that. But one of our key insights is that you really don't have to. Well, the one property that we really care about here is that if L.call is invoked, this callback is invoked with some value L, then in the past there exists a S value representing this task such that unsubscribe has not happened on that since it was returned by subscribe. And that listener object was the same as the subscription object. And so this is our second contribution, is a logic that expresses such things, callback control flow temporal logic, that specifies unrealizable framework behavior as needed. And then the next challenge is, can we automate proofs over this? We have our specification of unrealizable framework behavior. We have our message history logic. And we need to somehow figure out what is possible. And this boils down to what we call excludes initial checks, which will make sense in a little bit. But the main challenge here is that first order temporal logics are usually undecidable. And so making this perform well is a major challenge. And so the contribution is this automatic excludes initial check. And we use SMT solvers in a decidable fragment of logic called extended EPR. So first we'll dive into this control flow without the whole program using message histories. So how do we abstract message histories? We do a goal-directed analysis starting with an error condition just before the assertion failure. And this OK hist thing represents all of the message histories that we have specified as realizable, such as a subscribe and then a call with some other messages intermixed. Also, all the prefixes of a realizable message history are also realizable in this context, like the empty message history. And that's the initial starting point of the program. And then we compute the abstract states backwards around the callback, or along the callback control flow. And we have this funny notation with a double arrow here that's an ordered linear implication. And the idea here is that call is conceptually appended, and if that is a realizable message history, then the message history that you appended it to is realizable. And so this conceptually removes the call from that previous realizable message history, and it allows us to consider these backwards through the program. But importantly, this excludes the initial message history because you can't just have a call in the application. This would correspond to a task finishing that was never started. And so this is how we maintain precision, because a normal analysis here would have to have an alarm. It would have to just say, I don't know, I got to the framework, I don't have this code. And so the overall idea here is that the execution must have begun with the initial empty message history. And proving this excludes initial is how we handle the maintaining precision there. So overall, how does this work? At this point, we continue overall the different callbacks, and the abstract message histories continue to be appended. How this works is very interesting, so I recommend looking into the paper to see the details. But it ends up that these abstract message histories can be merged automatically. And that means we reach a fixed point, or we often reach a fixed point here. And if the whole invariant that we found excludes the initial, or excludes the empty message history, then the assertion must be safe, because we don't have a way to get from the start of the program to the failure. And so next we'll talk about a little bit about how we specify these things. And the main question that we're answering is we have an abstract message history, and we want to say, is this the initial point of the execution in the Android application? And so we say globally, if call has happened, if this message has happened, then in the past, yesterday, for those who are familiar with past LTL, this formula holds. There exists an S value such that unsubscribe has not been called since subscribe. This is the same one I was talking about earlier. And so this history implication models one callback and two call-ins, and it uses a fragment of past LTL that is enough to capture what we care about. But importantly, this allows us to reason about 3 methods rather than 10,000 callbacks and 100,000 call-ins. And most of the behavior of the framework can be soundly ignored. So next, we'll talk about automating decisions about this. And so I've introduced 2 funny-looking arrows here. And what this comes down to is that they combine and cancel each other out, because we say if a call has happened, then this is true, or a call happens in the future. And then the right-hand side of this figure is what we actually have to reason about. And so to make a long story short, we just have to reason about equality of messages and disequality. And this falls into the category of something that SMT solving is very good at, and in particular this extended EPR logic fragment. So finally, let's take a look at the empirical evaluation. So we started by looking at two apps that document their issues and fixes extremely well. Both apps that I use and watch the issue trackers and watch what kinds of things they run into and how they fix them. So we have 5 issues here that we selected based on things that alter the callback order by adding or removing method calls. And first we asked, could an analysis that has no callback order prove the buggy version safe? And for a few of these, we talk about distinguishing, which is proving the buggy ones, or proving the fixed ones safe and alarming on the buggy ones. And so the no order obviously alarms on all the buggy ones, but it also alarms on all the fixed ones, so this isn't terribly interesting. Then we have the approach of trying to model everything up front. And as you can expect, this is also not great. We find more cases where this proves the buggy versions, so it's unsound. And then Historia, our tool, with targeted modeling, we're able to distinguish all of these. And we find that the number of history implications that I showed earlier, we don't have to write that many. And also, it tends to reach that fixed point I was talking about rather quickly. So to extend this experiment, we went on to open source F-Droid App Store and got 47 apps with 2 million lines of code and found error locations. And we found that 43% were proven safe within an hour. Then we took 8 samples and were able to prove 3 of these by refining the callback control flow and found 1 true bug, and then 4 were timeouts. And then finally, we have 3 of these assertions, and we wanted to look a little bit closer at how hard it is to write the model. So we have the total callbacks and total call-ins, and what we find is that over 95% of the framework does not actually need to be modeled in order to prove these properties safe. So thanks, everyone. And just a note, I'm on the job market looking for industrial research jobs if anybody is interested. Thanks.
Very much, Shawn. Questions? We have time for 1 or 2. So I might have a question. So what was the average length of these history traces that you are considering? Like how long do is the verification effort in essence also, right?
Yeah, so we tracked the number of callbacks deep that it had to explore before reaching a fixed point, and that was typically on the order of like 3 to 5 callbacks. So it reaches the fixed point rather quickly. When there's an alarm, we get 6 to 8 callbacks typically. A lot of that's due to the sparse framework modeling that allows it to be that short. And they tend to be very useful counterexamples is what we found too. So.
Okay, thank you very much. Yeah?
Thanks for a great talk. Do you think that there's a way to synthesize or extract these specifications somehow from, for example, logs, doing something like model learning, or trying to somehow figure out in what order different things could happen?
Very good insight. That's the paper I'm working on next, and we already have a prototype that is starting to work. So yeah, that's the idea, is that they're relatively simple specifications, and the hope is that program synthesis can help us figure out what is the framework doing without having to go and read many thousands of pages of Android documentation. So yeah, good insight.
So thanks again, Shawn.